we've got a linear charge distribution. I've drawn it on the x-axis as this red line. So it has, the only dimension it has is length. The width here is insignificant. And we're trying to find the electric field due to this linear charge distribution of uniform charge density. And because it's a linear charge distribution, or we can call it a linear rod, we know that uniform charge density means uniform lambda, uniform linear charge density. And we're going to try to find the electric field due to this linear rod of uniform linear charge density at this point P, at some point along an axis. I've labeled it the y-axis that bisects the rod and is perpendicular to the rod. So let's start with a couple things that we know. So some things that we know: the total charge of the rod is Q, right? And so sometimes you might see people write it as a lowercase q. Whether you write it as an uppercase Q, lowercase q, it doesn't really matter. I tend to write the total charge of the rod as an uppercase Q and then write my dq's with a lowercase q. But you could also write it as dq with the uppercase Q. Either way works. The total length of the rod is 2L. So that's something you want to keep in mind, is that the rod goes from x equals negative L to x equals L. So L is actually only half the length of the rod. And it's a uniform linear charge distribution, right? Uniform linear charge density. So we also know that lambda equals dq over dx. Now, lambda always equals some infinitesimal charge, portion of charge, dq over some thing of length. Usually it's like dl, or if it's a circle, then we do ds for that arc. So I've just made the dl be a dx because our length is along the x-axis here. And because it's uniform, we also know that that lambda, the linear charge density, is equal to the total charge of the rod, q, divided by its total length, 2L. So this is a relationship that we want to keep in mind. So to tackle these kinds of problems, what we want to do is we want to imagine dividing up the charge source, in this case the linear rod, into an infinite number of dq's. So let's imagine picking a dq right here, right? And let's draw its dE vector, its infinitesimal electric field vector. I'm trying to draw a straight line here, and then we've got its dE pointing off something like this, right? And what we want to do is then imagine what the other d, and this is dE. Let me label. This is dE. Maybe I'll do it actually above it. Give myself some room. So this is dE. And then what we want to do is we want to imagine picking other dq's as well, right? So technically we want to imagine all the dq's, but let's just pick a few, right? If we pick this dq, right, another dq here, then we get a dE that looks something like this. And if we pick another dq right here, then we get something a dE that looks like this, right? An infinitesimal electric field vector due to that infinitesimal portion of charge dq. And then if we pick another one, let's say over here, right, the counterpart of this dq, then we get something that looks like this. And just by looking at this visual, we can imagine, moving along the rod from x equals negative L to x equals L, and imagine the dE vectors at point P, which is at a height of y, so the y is a constant here. And we can see that the x components of their vectors cancel, right? The x component of this turquoise one cancels the x component of the orange one, and likewise for the pink and green ones. But their y components add. And what this tells us is that we expect the net electric field at point P to look something like this, just some electric field vector whose only component is a y component. So this is what we expect the net electric field at point P due to this rod to look like. So now what we want to do is we want to come up with an equation to describe the magnitude and direction of this electric field vector. We want to come up with an equation that basically gives us this net electric field vector at point P. And to do that, we're going to have to first work with we're going to have to pick a dq, and then we're going to have to start working with it and working with the relationships that we can see to get it into something that we can integrate, that makes sense to integrate. And that'll hopefully in the end give us an equation to work with. So as we do with these types of problems where we're slicing up some charge distribution into an infinite number of dq's, what we first want to do is break down the dE vector into components. So, and yeah, let's continue the orange color. So we've got dE is equal to, and then its components are its x components, right? dEx plus dEy. And again, I'm just getting this from the components right here. So this is dEx right here. And then this is dEy right here, right? And we also want to keep in mind that this angle here, I'm trying to find a color. I've used this color. This angle is theta, and that's the same angle as this angle right here, the angle between this imaginary dotted line to the DE and the x-axis here. And this distance is r, and this distance is y, right, from here to here. So we want to keep in mind the triangles that we've got going. So we've got a right triangle right here, right triangle right here, and we've got another one up here formed by the components of DE, right? DEx, kind of small, but I'm just trying to make sure we've got everything labeled, and then DEY. And let's see, and then we have to have the distance from our DQ to the origin, which we just call x, right? So we've got two triangles going on. We've got this one going on here with side lengths of x, y, and r, and we've got this triangle over here with side lengths of DE, with whose sides are vectors, the components of DE, and then DE itself. So after that, let's just continue breaking down the 1DE. So as we do in these problems, we pick one DQ and then work with that one DQ and the DE due to it. And the reason why we can do that is because the math that we do with the DE due to one DQ also holds for any of the other DQs. So you don't have to pick this DQ. You could pick a DQ over here, and all of these relationships and all of the breakdowns of these vectors would still hold the same. You might get an opposite direction for the unit vectors, but in the end, everything will come out the same. So then what we want to do is we want to look at the triangle formed by this guy. And so DEx, the x component, is going to be DE, the magnitude of DE, and cosine theta, and then I hat plus, and then DE sine theta j hat, right? We're just looking at this triangle up here. So if I want to quickly redraw that triangle, we get something like this. Let's use the light blue color. So we've got DE right here, we've got DEx, and then we've got DE. Let me make this triangle bigger. We've got DE right here, we've got DEx, and then DEy. So again, I'm just breaking down the vector into its components right here. DEx, DEy, DE, and then we've got theta. So I'm just working with this triangle right here, as we generally do when we're working with vectors and breaking them down into components. And then what we want to do is we want to rewrite this DE. So what you want to do is you want to remember the equation for the electric field due to a point charge, because we're going to treat the DQs as point charges. So for a point charge, it's the magnitude of the electric field that it creates is, let me rewrite this, KQ over R squared, right? This is for the magnitude of the electric field due to a point charge, and really it's the magnitude of Q. You could write absolute value bars around this Q, but I'll just leave the absolute value bars off. And what we want to do is then we want to rewrite this in infinitesimal form. So if Q is an infinitesimal point charge, it's a dQ, then the magnitude of its electric field is dE, and it's due to that dQ, right? So K times dQ over R squared, the distance from the dQ to the point you're finding the electric field at. So knowing this, we can rewrite these dEs. So let's go ahead and do that. And I'll try to write a little bit more so that we have, over to the sides, we have some more room. K dQ over R squared cosine theta I hat plus K dQ R squared sine theta j hat. And then what we want to do is we want to rewrite the cosine thetas and sine thetas in terms of the other variables that we've got going on here. So to do that, we want to look at this triangle right here. So let me scroll down a bit and make that triangle a little more obvious. So we've got this triangle, something like this, and this is y, this is x, this is r, and then point P is up here, and then our dq is right here, right? dq is over here. So looking at this triangle, and then this is theta right here. So looking at this triangle, which is just this triangle right here, we see that we can rewrite the cosine thetas and sine thetas in terms of like x over r and y over r. So let's go ahead and do that. dE is equal to k dq over r squared. So the cosine theta is going to become x over r, right? Adjacent over hypotenuse. K dq r squared. Sine theta is going to become y over r, opposite over hypotenuse. And then we can combine these fractions, right? Multiply their r's together. So we get kx dq over r cubed I hat plus, and then we get ky dq over r cubed j hat, right? So from here, what we want to do is if we were to integrate both sides, we'd be integrating in terms of dq, which would just be, the limits of integration would just be from 0 to q. That isn't really helpful. That doesn't really help us solve this integral because x is changing, right? Although we do know that the x component is going to cancel out, but the r is changing. It's different for different dq's as we move along the rod. So integrating from 0 to q isn't helpful. We want to rewrite the dq in terms of some other infinitesimal something else, d something else that we can actually integrate in terms of. And that's where we use our lambda relationship, the y equals dq over dx. So we know that, and again, I'll continue kind of writing our side notes over here. So we know that lambda is equal to dq over dx. So thus we also know that dq is equal to lambda dx. So let's sub this in. So subbing that in, and I'll just continue writing in yellow here. dE is equal to k, let's see, kx lambda dx over r cubed I hat plus ky lambda dx over r cubed j hat. And now what we want to do is we want to rewrite the r, right? So using the Pythagorean theorem, just looking at this triangle, right? We know that r squared equals x squared plus y squared. So we know that r is equal to the square root of x squared plus y squared. Sorry if that's getting really small, which we also know is the same thing as being raised to the, I'll try to write this a little larger so that I'm not so much in the corner here, x squared plus y squared to the 1/2, right? Writing the square root is the same thing as raising it to the 1/2 power. And now we're going to sub in, so this is r right here. So r is x squared plus y squared to the 1/2, but then we're going to cube it when we sub it in for r cubed. So r cubed is going to be this raised to the 3rd power, right? To the 1/2, and then we're going to be cubing this. So then you just multiply the powers. So you get that r cubed is equal to x squared plus y squared to the 3/2. And we're going to sub in this r cubed. So that gives us, and I'll just continue writing out like this. So dE is equal to kx lambda dx. Subbing this in, we get x squared plus y squared to the 3/2 I hat plus ky lambda dx over x squared plus y squared to the 3/2 j hat. And now what we want to do is, now that we've gotten things, now that we've got a dx is something that we can definitely integrate in terms of, right? Because the only variable here that isn't changing, or that is changing, is the x, right? The distance between the origin and the dq, right? As we integrate from x equals negative L to x equals L, we're picking all these different dq's and adding together all of their different dE vectors as we move along. And so we can definitely integrate in terms of x. X is the variable that's changing, and it's also the infinitesimal bit that we've got our expressions in terms of, a dx, right? So we can integrate this now. And from before, we know that when we integrate the x component, which is this term right here, that the x component is going to become 0, right? Integrating that x component will give us the x component of the net electric field vector, which we see has no x component, right? We visually saw that all the x components will cancel. So when we integrate this term, this should become 0, right? So let's just go ahead and show that. So we know that E, the total electric field vector at point P, is going to be integrating dE, and we're going to be integrating from negative L to L. Sometimes you may not see the limits of integration written because it's just conceptually integrating dE, you're adding up all the dE's, but this is technically where we're integrating from, negative L to L. And this is going to be equal to integrating, right? We're going to be integrating this right side of the equation, which is the same thing as integrating each individual term. So it's going to be negative L to L kx lambda dx over x squared plus y squared to the 3/2, and then plus the integral of negative L ky lambda dx over x squared plus y squared to the 3/2. And this integral involves trig substitution, which I'll show in another video when we don't want to forget the unit vector direction. So we've got I hat and j hat. So integrating this vector on the left here, which you do using u substitution, you'll see that this becomes 0, right, as we showed visually above. And then to integrate the vector on the right here, you end up having to use trig substitution, right? So what you end up getting is you get E is equal to, and then you pull the constants out. So k, y, and lambda and j hat are all constants. So you pull them out, and lambda is a constant because it's a linear charge density, right? When you have a linear charge density, the charge density is just a number followed by a unit. It's a constant for the entire charge distribution. So then we get negative L dx over, and then we get x squared plus y squared to the 3/2. And in order to integrate this integral, we end up having to, as I said, use trig substitution, which I'll show in another video, but you can also just remember this formula to do it, and this formula just comes from trig substitution, but I'll just show it right here. So we get 1 over x squared plus y squared. Here, I'll show this as an a squared actually. X squared plus a squared to the 3/2 dx is equal to, and it's 1 over a squared x over the square root of x squared plus a squared, right? And evaluated from b to a. So this is a little formula that I'm going to use, and I'll show how we get this formula in the next video. But from here, we can simplify this integral. So a is a constant, which in our case is y, and x is the variable, which in our case is also just x. So let's continue evaluating this integral by what we've got here. So we get ky lambda j hat, and doing this, we get, okay, so it's going to be 1 over y squared, right? And then x over the square root of x squared plus y squared, evaluated from L to negative L, right? We're almost here. So we've got E is equal to, so first we can see that we have a y up in the numerator, and then we have a y squared down in the denominator. So we know that one of those y's is going to cancel. So we get ky j hat over y, that's the front. And then to evaluate the back end, we're going to have to plug in the l's, and we're plugging in the L and negative L into x. That's the variable that we integrated in terms of. So you want to be careful about which variable you're plugging in, because remember, y is a constant. We integrated in terms of x, so the limits go in for x. So we get L over square root of L squared plus y squared, and then minus, plugging in the negative L, we get negative L over square root of L squared, right? Negative L squared is L squared plus y squared, and minus minus is the same thing as adding ky j hat over, let's not get sloppy, ky j hat, or at least a little less sloppy. So then we add these two together, so we've got L plus L over square root of L squared plus y squared. So we get 2L, and this is a parenthesis, So we get 2L in the numerator, right? 2L k lambda j hat over y square root of L squared plus y squared. And you could say we're done here, right? We found the equation. This is the equation that we could use. But there's another little trick that we have. Remember that lambda is equal to dq over dx, which we said because lambda is uniform is the same thing as having q over 2L. So let's look at lambda equals q over 2L. Multiplying both sides by 2L, we get lambda, let's see, 2L lambda is equal to q, right? And we look in our numerator, we have a 2 times L times lambda, same thing we've got going on here. So we can replace it with a q. So let's do that. So we've got E is equal to, and then the 2L lambda go away, replaced by q. So we got k, q being the total charge of the rod, over y times the square root of L squared plus y squared, right? And then our unit vector j hat. And we're done. This is the equation. This is the equation that gives the net E that we found up above at point P, right? That gives this sort of hot pink vector that we have up here. And this is the equation that does it. So you might be wondering, like, you might also, so a question that often arises is like, well, what if the charge distribution is negative? We often solve for these equations in terms of the charge distribution being positive. Well, the same thing holds. It's just that all of the vectors switch directions. So all of the dE vectors would be pointing in the opposite direction, just flipped by 180 degrees. So up above, we showed that at point P, the net E vector would look something like this. Well, if the charge distribution was negative, it would just be the same thing, but it would just be pointing down by that same magnitude. So all that would change in this equation is that there would just be a negative j hat, right? So which would just translate, maybe if you wanted to move the negative, to a negative out here. But either way, it's the same equation except for just the direction of this E, this net E vector just reversing. And another thing to keep in mind when you're using this equation is, again, that the total length of the rod is 2L, right? Not L. So to plug in for L here, you need to divide the total length by 2. L is half the length of the rod. But other than that, we're done.